Hello everyone, we're going to be going over section 8.1, which is on right angle trigonometry and its applications. So we have four objectives for this section. Objective 1, we want to find the value of the trigonometric functions of acute angles using right triangles. 2, we want to use the complementary angle theorem. 3, we want to solve right triangles. And 4, solve applied problems. So jumping right in with objective number 1, we want to find the value of trigonometric functions of acute angles using right triangles. So a triangle in which one angle is 90 degrees, or a right angle, is called a right triangle. The side opposite of the right angle is called the hypotenuse, and the remaining sides are called the legs of the triangle. So it should be a little bit of a review here from geometry. If we label the hypotenuse C and the legs as A and B, then we can use the Pythagorean theorem, which then tells us that the sum of the squares of our legs is equal to the square of our hypotenuse. Or in other words, a squared plus b squared is equal to c squared. So now this is telling us that each side of our triangle, when they're squared, their sum is going to be equal to just the square of the hypotenuse. Then an angle is an acute angle if its degree measurement is going to be between 0 and 90 degrees. And this is a strictly greater than and strictly less than. So greater than 0 and less than 90. Or a radian measurement of greater than 0 and less than pi over 2. So if we look at our image here, we see we have a triangle. It has our right angle right there. That's usually what we interpret when we write a square there in the corner of those two lines. That's our right angle. That's always going to be 90 degrees. So we have our triangle. Our long end is our hypotenuse C. We see it as opposite of the 90-degree angle. Then we have here our angle theta, and from theta we see that side B is opposite and side A is adjacent to theta, not our 90-degree angle, just theta. Then over on our right side we have a very similar image there. This is now just to say that we can use the Pythagorean theorem, and if we place this on the xy plane, that upper point would end up being the point A, comma, B. So the length of A and then the height essentially of B. So by referring to the lengths of the sides of the triangle by names the hypotenuse, opposite, and adjacent, we can let the trigonometric functions of theta, or the acute angle, once again, not the right angle, the acute angle, be expressed as ratios of the sides of the right triangle. So we see we can rewrite our trigonometric functions that we learned in our last few sections into explanations of triangles at this point. So when we have sine of theta, this is going to be equal to opposite over hypotenuse, or the length of B over C, if we're looking at something like the triangle that we're given here, or the right triangle that we're given here on the left. Then cosine of theta would then be adjacent over hypotenuse, so that would be the side length of A over the hypotenuse. Then with tangent of theta, that's going to be opposite over adjacent, so that length B over A. Then cosecant of theta, which is the hypotenuse over the opposite, which is the hypotenuse C over the opposite, which is B. Secant theta is the hypotenuse over the adjacent, so we have C over A, where we see our hypotenuse over our length that is adjacent, and then cotangent, we have adjacent over opposite, so we have our length A divided by our length B. So we see the same kinds of patterns here. We see that cosecant, secant, and cotangent are all going to be reciprocals of sine, cosine, and tangent, respectively. Another way that we can remember which goes with which is a saying that you might have heard of before, which is remembering SOHCAHTOA. So let's write this over to the side. So it's SOHCAHTOA, and we write SOHCAHTOA to remember that when we have sine, it's going to be opposite over hypotenuse. I'm not very good at writing vertically. Then when we have cosine, we have adjacent over hypotenuse. And when we have tangent, we have opposite over adjacent. So, and then when we have cosecant, secant, and cotangent, we know it's just going to be the reciprocal of these terms. So the easiest way to remember would be remembering it this way. So remembering SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. All right, so let's go ahead and try and find the exact values of the 6 trigonometric functions of angle theta based on the triangle below. All right, we see we have our triangle here, and we have a right triangle, we see, because it has the square here in the corner. So we know that this is 90 degrees already. Then we have theta written out in this one corner, and we have our hypotenuse, which is going to be 5. So you can write C is equal to 5, and our adjacent value is equal to 3. So what we want to do now is we want to find the exact value of our 6 trigonometric functions of angle theta based on the triangle below. So things that we can already find. We know that we have adjacent and we have the hypotenuse. So we could already find cosine and secant immediately because these are what are required of us. But we want to find the value of the opposite. And in order to find the value of the opposite, we can go ahead and use our Pythagorean theorem. So let's write that. To find the value of the opposite length, which we call B, we can use the Pythagorean theorem. So we know our Pythagorean theorem states we have a squared plus b squared is equal to c squared, where we have our values of a and c. So if we plug those in, we get 3 squared plus b squared is equal to 5 squared. Then 3 squared is 9 plus b squared is equal to 25. We subtract 9 from both sides. When we do, we get b squared is equal to 16, where the square root of each side gives us b is equal to 4. Yes, we know that the square root of 16 is technically positive or negative 4, but since we're working with things like triangles, we're not going to have negative lengths. That also just doesn't really make a lot of sense. So we don't have any negative lengths, so whenever we find these values, they're always going to be positive unless specifically stated otherwise. So now we found our value for b. So now we have all our values. We have a is equal to 3, b is equal to 4, and c is equal to 5. And now we have all the values we need to find our values, or the exact values of our 6 trigonometric functions. So starting off with sine of theta, we know that sine of theta is going to be opposite over hypotenuse. since we're going to write it so many times, opposite is going to be OPP, hypotenuse will be HYP, adjacent will be ADJ. So sine of theta is the opposite over hypotenuse, which in this case is going to be B over C, which is the value of B 4 over 5. Next, we have cosine of theta. Cosine of theta is adjacent over hypotenuse. So we have adjacent over hypotenuse, which in our case is going to be A over C, which is 3 over 5. Now we can do tangent of theta, which is opposite over adjacent. So we have, in this case, B over A. So this gives us 4 over 3. And now we have our reciprocal functions. So we have cosecant of theta. Since we know it is the reciprocal of sine of theta, we could just say, oh, it's going to be 5 over 4, because we know that sine of theta is 4 over 5, which that is the correct answer, but we're going to write it out just as we did before. So cosecant gives us our hypotenuse over the opposite, which will now be C over B, which we know is now going to be 5 over 4. Then we have secant, or reciprocal of cosine. It's going to be our hypotenuse over the adjacent. So this will be C over A, which gives us 5 over 3. And lastly, we have cotangent of theta, which is the reciprocal of tangent. So we get adjacent over opposite, which gives us A over B, which is equal to 3 over 4. And these are our final values. We have sine of theta is 4 over 5, cosine of theta is 3 over 5, tangent of theta is 4 over 3, cosecant of theta is 5 over 4, secant of theta is 5/3, and cotangent of theta is 3/4. So those are the exact value of the 6 trigonometric functions of angle theta based on the triangle that we were given. So if you ever have problems like these where you're given 2 side lengths, all you really need to do is use the Pythagorean theorem to find that last side length, and then use our definitions for our different trigonometric functions in order to find their exact values. So all right, moving on to objective 2, I want to use the complementary angle theorem. So 2 acute angles are called complementary if their sum is a right angle or 90 degrees. So the 2 acute angles in a right triangle are always complementary. If we have a right triangle, we know that all triangles have to be equal to 180 degrees. And if we have a right triangle, that means that one of those angles has to be 90 degrees, which means our other 2 angles have to also equal 90 degrees. So whenever we have a right triangle, and we know that we have a right triangle, we can also assume that our other 2 angles will then be complementary. So they will add up to 90 degrees. So referring to our figure here on the right, the angle that is opposite to side B is going to be labeled capital B, and the angle opposite to side A is labeled capital A. So this is how we're going to label our different angles, which are now according to our different sides. So our hypotenuse, or C, is now going to refer to our right angle, where now our side lowercase a refers to our angle capital A, and our side lowercase b refers to our angle uppercase B. So we can highlight these, see B and B, A and A, and then we can just say C and 90-degree angle, or a right angle. Then this also makes side B adjacent to angle A and side A adjacent to angle B. So let's say that one more time, just a little bit confusing. We see side B is then adjacent to angle A, and side A is adjacent to angle B. if you're given a triangle and you're told what sides are which, it's fairly simple to decide which one's going to be adjacent, which isn't. But as a standard practice, this is kind of where we go from. Which then this gives us this result. So working with our complementary angles, we have that sine of B, so sine of angle B, which is then equal to B over C, is equal to cosine of A. So we see that that's how our complementary angles then work. Then we also have the cosine of B, which would then be A over C is equal to sine of A. Tangent of B is equal to B over A, which is then equal to cotangent of A. Let's zoom out a little bit so we can actually take a look at that. Cosecant of B is equal to C over B, which is then equal to secant of A. Secant of B is equal to C over A, which is equal to cosecant of A. And cotangent of B is equal to A over B, which is then equal to tangent of A. So we're just seeing here how certain ratios are going to relate to the angles that we see on our triangle. Now we have that because of their relationships, sine and cosine, cosecant and secant, and tangent and cotangent are going to be called co-functions of each other based on what we just went over. So if they're co-functions, this means that their complementary angles or co-functions of complementary angles are going to be equal to each other. So some examples of this would be complementary angles would be sine of 30 degrees is equal to cosine of 60 degrees. We see our complementary angles are 30 degrees and 60 degrees since they add up to be 90 degrees. Our co-functions are sine and cosine. In our next example, complementary angles would be 40 degrees and 50 degrees since they add up to 90. Co-functions in this case would be tangent and cotangent. And then in our final example, complementary angles would be 80 degrees and 10 degrees since they add up to 90 degrees, and their co-functions are secant and cosecant. So for our example, we want to use the complementary angle theorem in order to find the values of A, sine of 62 degrees, and B, tangent of pi over 12. So starting with A, we have sine of 62 degrees. First off, let's identify what our complementary angle is going to be. So the complementary angle of 62 degrees, we know that this value has to add to 62 degrees in order to become 90 degrees. So in other words, if we subtract 62 degrees from 90 degrees, that will give us the value of our complementary angle. So let's go ahead and do that. So 90 degrees minus 62 degrees is going to end up giving us 28 degrees. So our complementary angle is 28 degrees. Now the function we're working with the sine, so the cofunction of sine is going to be cosine. Let's actually move this up a little bit. So the cofunction of sine is now going to be cosine. So this tells us that if we have sine of 62 degrees, which is the same as saying 90 degrees minus 62 degrees, or 28 degrees essentially, this is going to end up, let's write this out a little bit more. We'll expand it a bit. So we have sine of 62 degrees. This is now going to be equal to cosine of 90 minus 62 degrees, which is just equal to cosine of 28 degrees. So we're stating that these values are equal in this case. Actually, we'll just write sine again below. So we're stating that sine of 62 degrees is equal to cosine of 28 degrees. Now for B, we have tangent of pi over 12. So first things first, let's find the complementary angle of pi over 12. pi over 12. So if we're working in radians, we know that the equivalent of 90 degrees is going to be pi over 2. So we're going to subtract pi over 12 from pi over 2 to see what our complementary angle is. So we have pi over 2 minus pi over 12, which we want to have the same denominator, so we'll alter pi over 2 to now be 6 pi over 12 minus pi over 12, and this simplifies to 5 pi over 12. So now we know our complementary angle. The complementary angle of pi over 12 is going to be 5 pi over 12. Then our cofunction of tangent is cotangent. So now we know our cofunction and we know our complementary angle. So when we write this out, we're going to say tangent of pi over 12 is equal to cotangent of pi over 2 minus pi over 12, which now will simplify down to be cotangent of 5 pi over 12. So now we're stating that these values are now going to be equal since we use the combination of our cofunctions and our complementary angles.